A couple of announcements before we start. So there's an error in one of my handouts, and I didn't realize it while I was talking about it. One of the extracellular concentrations, and we're basically going to be doing mostly audio recordings. When you look at osmolarity, little m, big O, SM is milliosmolar, so it's redundant to have /L. What that should be, there's two ways to write this, and I made a mistake. So this is milliosmolar, or what you could do is 4 milliosmoles per liter. That's what it should look like. So you either get rid of the L, and when you see a big O, it's osmolar, right? So this is the difference between molar versus moles, right? Only it's osmoles versus osmolar. So just, it's a quick correction. It looked like this. That's incorrect. Sorry about that. I didn't catch it when we were talking about it. I fixed it everywhere else. I've actually already fixed that sheet online in Eraser for you. So if you wanted to print out one that's fixed, I don't think you need to kill another tree. So that's a little mistake. Okay, so I'm recording this. I'm using Camtasia right now. It didn't work the other day, by the way. If you didn't see another Camtasia, it's because there was something going on with the internet here. I had all kinds of problems in both my classes. It didn't work. Today it's working. So this is basically recording. Okay. So before we start, as per tradition, where were we last time? What did we do? Big things. And then I'm going to talk to you about the types of answers. So give me the answers first, and I'm going to talk to you about the types of answers I'm looking for and what the cue is going to be on answers. Okay, big things we did. You can look at your notes, Laura. The differences in intracellular and extracellular concentrations, I said just memorize. Okay, that's important. What else? Electrochemical gradient. What else? Diffusion, yeah.
Difference in charges and extracellular.
Difference in charges, huge. Okay, Laura. Plateau, right? We talked about a transport and non-transport. Okay, I did this in my anatomy class last semester. Something I went to a teaching conference in Buffalo, New York, last September. I brought this back, and we used this a little bit. Those of you who haven't had me for a while, have never had me, you've never seen this. Okay, so when I ask for an answer, when we're talking about, the beginning of the lecture, the end of the lecture, people generally give me generalities. Okay, it's an easy one to give. So I'm going to talk about 3 people real quick and associate characteristics with each of those people. And then from this day forward, when I mention that person, you'll know, oh, that's the kind of answer he wants. Okay, so the first person, we did this, right? The first person is Yogi Berra, not Yogi Bear. Yogi Bear is a cartoon character. Yogi Berra is a Hall of Fame catcher that played for the New York Yankees in the 40s and 50s. Okay? Now, Yogi Berra was a very simple man. You look him up online, he has lots of famous quotes. They're almost too simple. He was a very simple man. There's sort of broad topics, big generalities. So if I say, okay, give me what we did yesterday or the last lecture, somebody give me a Yogi Berra answer. You're going to give me a big, broad category. Like the first one, Laura, the table, intracellular and extracellular concentration. That's pretty broad. The second person, we're going way back here in history. The second person, whose name is Howard Cosell. Howard Cosell was the premier sportscaster for ABC during the 60s and the 70s. If you go on ESPN, they have Battle of the Network Stars, which is an old thing they used to do between ABC, NBC, and CBS before Fox even existed. And they had all the stars in the battle. The guy that's announcing for them, and it's on like every night, so if you want to take a look at Battle of the Network Stars, is what people look like. Anyway, the guy announcing is Howard Cosell. Howard Cosell was a real mechanistic type of guy. In other words, he was he would give you answers and analysis that were clear and concise. Not too general, not too complicated. That's what made him famous. He was sort of a matter-of-fact guy, but he gave you enough detail when he gave you an analysis of whether he was doing boxing, because boxing was really big in the United States up until the early 80s, and then it sort of went away. So that's a Howard Cosell answer. So a Howard Cosell answer is sort of the next level down in complexity. So when I say Howard, I want a Howard Cosell answer, you're going to be like, oh, okay, that's not just we did the electrochemical gradient. That's a Yogi Berra answer. Okay? And I'm not picking on here. The third level down is Aristotle. Everybody's heard of Aristotle, right? Great ideas, right? Great thinker, Greek thinker. Aristotle was all about deep, deep thought. So when I say I want an Aristotle answer, that's okay. How does that go? How do we go from electrochemical gradients, Yogi Berra answer, to Howard Cosell, to Aristotle? Aristotle is going to be a deep, complex answer. Now, you may not be ready to give an Aristotle answer, but now at least you'll know what I'm talking about. Yogi Berra, big picture. Howard Cosell, sort of mechanistic, a little bit of detail. Aristotle, give me an advanced biology class answer. Okay? That's our code. That's kind of fun too. Now you know a little bit about people you never heard about before. Okay? All right. So we talked about the mistake. We talked about, everybody got my email about the water. I'm so sorry. It's food. Not my rules. It's OSHA rules. So I've just been naughty. Even I can't drink my water. Okay. So we ended with osmolarity. Okay. We talked about, and let's go to this. So we're going to do mostly board stuff today. All right? But I'm just bringing this up because it makes it easier to talk about it. We'll go back to where we were. With this stuff. Right? Remember what we did? This slide and this slide. Okay. And this slide. Oh, is it not? Yeah, it's not. I forgot, I have to tell it. Oh, send to all. There we go. Yeah.
So our figures 416 and 417 not important. So we skipped over those, and 418. We didn't go over those three. We stopped right at the next one.
Oh, we didn't get here
We
yet.
didn't do 416.
Oh, yeah, I did it with the other. That's okay, yeah, no. Yeah. So because you're the only class that's going to have class with me on the 27th, the other two lectures are actually ahead of you on purpose. That's why. Okay. So we'll get through this and we'll still go back to the board. Good point. All right. Somebody want to just turn the lights down to here. Good. Okay. So let's look at this. In the diagram on the left, you have pure water. Okay? In the diagram on the right, you have water and solutes. Which one of these two is a better representation of what the water content inside your body is? The solution. That's right. Okay? So you're not made of pure water. Okay. All right, so here's an example. We're going to start getting into osmolarity and fluid movements. Okay? So in figure 417, the partition between the compartments is permeable to both water and solute. So the light blue and the purple dots can move. Okay? So we start off with a permeable membrane, two compartments. The osmolarity, this is osmolar, right? In the left compartment is 2. Okay. 2 osmolar. I like doing everything in 1 osmolar. This is osmolar. In the right compartment, it's 4. The water concentration in the left compartment is 53.5 molar. That's high. But that's the molarity of water. Okay? Give or take. The molarity of water in the right compartment is 51.5. The compartments are identical in size. Okay, we've been talking about the electrochemical gradient. There's an electrochemical gradient here. There may be more than one. Based on what you understand, or what we talked about, what is going to happen to the water? Somebody tell me about the water, and what's going to happen to the solute? You don't have to do both. You can do one or the other. Yeah, Teresa.
So water will move to the right equal concentrations.
Correct. That's what the arrow's up there, so it's not really a trick question, right? Right, because it's moving down its electrochemical gradient. Okay? It's moving down its electrochemical gradient. There's a higher concentration here of water, so it's going to move down it. Okay, now let's do it for solute. What's going to happen to solute? Yeah. So will it go in the same direction? It's going to go in the opposite direction. That's right. It's going to go in the opposite direction. Yes, Leonard.
Just out of curiosity, why don't you refer to the amount of solid as molarity as osmolarity instead?
Oh, it's just by convention, because most people are used to molar here, and we're going to go into osmolarity. That's because when you're talking about water, you're talking about something that is pure. Osmolarity is water plus solute. In here, you're dealing with pure water. So you can't really talk about pure anything as osmolar. Just like pure hydrochloric acid. You can't talk about hydrochloric acid as osmolar, right? So this is water. Good question. All right. So the water's going to move that direction, and the solute's going to move in that direction. In the big picture, the Yogi Berra answer as to why that's happening is what? Equilibrium. That's it. Perfect. Equilibrium. Now, what allows this to happen? There is a key statement made here that tells you that that's even possible. And what's that key statement? Somebody read it to me. Teresa.
Permeable to water and solute.
Yes, that is super important. It is permeable to water and the solute. That's the only reason that that occurred that way. So when the process goes to its normal end, right, you're going to end up with a compartment, each of which has the same osmolarity, each of which has the same molarity of water, and the volumes don't change. Okay, everybody's good with that. That's the easiest example you're going to see in the next 4 days. All right. Now, we have a different issue. But we start off with the same parameters. How is this one different than the last one? Yeah. Yes, this one is permeable only to water. This is just like your body. So your cells, right, your cell membrane, is permeable to water all the time because of those aquaporins, those water channels. But it is not permeable to salts, essentially ions. At least not all the time. So this is more like a real world example. All right, so the starting parameters are all the same. Okay, so let's start with water again. Okay, same situation, slightly different parameters. Okay, what's water going to do and why? Yeah, Leonard.
Water's going to move to the right, so it gets the equilibrium.
Water's going to move to the right, just like it did before, because its electrochemical gradient says that it should move from high to low. That's the same. Okay. What about the solute? Yeah, Colin.
Higher concentration slides to the right versus the left.
That's correct. So it's the same, higher concentration here than here. What's the solute going to do? Laura.
It stays on this one side because it's not able to be very.
Correct. It can't go through the barrier. We have a problem. Don't we? Because it wants to go to equilibrium. Okay? So this is what's considered causing a pressure. So the fact that those solutes can't move actually creates something called osmotic pressure. Osmotic pressure. So when you have solutes that cannot move, they create a pressure. That pressure is called osmotic pressure. Technically, osmotic pressure is the pressure that is exactly equal to the amount of pressure needed to stop water from moving. That's the technical definition. I have used that in the past, and I've gotten the same look I just got, which is total confusion. That doesn't really mean anything. Just know that when you have ions that cannot move, they create an osmotic pressure. Everybody okay with that definition? Go ahead.
So does that mean at a certain pressure, water can't move?
Yeah. It could. It could mean. If you actually wanted to figure out how much pressure you would have to create in this direction to stop water from moving. But we're not going to do that. It's an advanced topic, it's an advanced definition, but it's the real definition. The fact that these purple dots cannot move creates an osmotic pressure. Everybody with me? Okay. So there's a problem. Why is there a problem? What's the problem with this example? Based on everything I told you so far. Don't look at the answer at the bottom. Yeah, there's a problem, isn't there? Yes. Okay, so you made a jump, but you're thinking about it the right way. So Crystal said the solute will never reach equilibrium. That's not true, but because it can't move, it can't do anything about reaching equilibrium on its own. That's the problem. Okay, so how do you solve that problem? Well, then we go to the bottom. Here it's different. We eventually get to 3 milliosmolar, just like we did on the last one. We still get to 52.5 and 50.5 molar water. How is this one different? Look at what happened with the compartments. How do you do it? You have to change the size of the compartments. So to get to Crystal's point, in order for the solute to get to the equilibrium point, you're basically going to have to dilute it so that these are equal. And when you dilute it, water will go towards the solute because the solute can't move in the opposite direction. That's why the solute is called a non-penetrating substance. This is why when you give somebody a bag of saline, you give them 300 milliosmolar, which is neutral, because if you've just got a couple of gunshot wounds, okay, what does this mean? If you just had a couple of gunshot wounds, which of these scenarios would you want? We haven't gone to this yet. Would you want the cell to shrink or swell, or would you want the cells to just stay hydrated and roughly the same size? Yeah, because your body doesn't have the capacity when you had 2 gunshot wounds to regulate compartments very well anymore. We saw this happen with my pizza example, right? The pizza example said that if you start eating a pizza every day, right, or twice a day for a week, how long does it take for your homeostatic systems to fix that problem? 2 to 3 days. Does a gunshot wound victim have 2 to 3 days to have a fix? No. They may have minutes. Okay? So that's one of the reasons why you do it. This happens and your body has to deal with it. But if you're very, very sick, this is a stress you don't need. Okay? Did anybody not follow any of that? What happened? Why did water move? Right? The water moves because it goes down its concentration gradient. How much it moves is based on how much solute is there, and that will determine how the shift in compartments occurs. Yeah?
So it will move down until the osmolarity is the same, or is that just the same?
No, it will move down. This here,
Yeah.
this is the end result.
Right.
That's what it wants.
That's
So it got to the same result here. The difference is here the compartment didn't change. Here, same answers, but the compartments have to change. This is what happens in real life. This is what happens to your body. The cells swell or shrink. And that is stress that your body has to deal with. You're all young, you're all healthy, it's not a big deal. You have a gunshot wound, it's a big deal. Everybody with me so far? Okay. We're going to go to, this is the last slide, and then we're going to start doing stuff on the board. Okay, so I'm going to introduce you to the first of two sets of terms when we're talking about osmolarity and the cell changing size and shape. Okay. The first one is about tonicity. Okay, that's why these terms end in tonic. Okay, you have a hypertonic solution, an isotonic solution, and a hypotonic solution. Right? Everybody with me so far? Okay. What is the give or take ballpark, or the number we're using if you've already memorized, osmolarity of your body? 295, so roughly 300. Okay, so when you take that bag of saline, let's do an experiment actually. We're going to take a bath and we're going to put a 300 milliosmolar solution, right? So it has a certain amount of stuff in it that gives it the 300 milliosmolar. Then we're going to take one of your body cells and we're going to stick it in the solution. Okay? No change in the cell volume. That's called an isotonic solution, which means that the tone, the number of molecules here per square inch is the same as the number of molecules here per square inch. The total number of molecules may be different, but that's not what your body keys in on. So they have the same tone. So that bag of saline that the hospital gives you, IV, is an isotonic solution of non-penetrating solutes. That's an important. Non-penetrating solutes. This is the simplest version. Okay, now we're going to do another experiment. We're going to take that same cell and we're going to put it in a bath that has a 400 milliosmolar molarity. Okay? Is that greater or less than or equal to that of your body? Greater. Okay. So that means that per square inch, per square centimeter, however you want to think about it, there are more molecules. Ultimately, there are more molecules here than here, but that's not what counts. It's the relative amount of molecules. Per square inch, there are more here than here. Okay. Go back to the last example. What ends up happening, if you're in Professor Greening's course, she'd say just memorize it. In a hypertonic solution, the cell shrinks. Okay, that's easy. Anybody can do that, pass the test, and totally forget about it and not understand it. I want to know why the cell shrinks. Colin.
Water leaves the cell about the rate of higher solute concentration.
Say that. You guys speak
The
louder.
water will leave the cell towards the area of higher solute concentration.
Yes, so the water will leave the cells in the direction of the higher concentration of solutes. But this goes back to the answer that Alexis has already given. And we're going to go back to you. The answer was why? What is the body looking for?
Oh,
Equilibrium or homeostasis, right? Homeostasis or equilibrium. Equilibrium is, it wants equilibrium, but it will kill it. So, but it wants it anyway. Okay, Colin's saying that the water is going to move out to the higher number of particles. If you think about it, if there's a higher per square inch number of molecules in the bath versus the cell, where is there a higher concentration of water in this particular case? In the cell or outside the cell? Max? In the cell. So essentially what Colin is saying is the water is going down its electrochemical gradient. The way he's thinking about it is the way I think about it as a physiologist, is whenever I see a high osmolarity, I think about it as a dilution. The particles can't move in because they're non-penetrating, so the only way to make this thing work is for the water to move out. If you're thinking about it from a chemical perspective, it's the water concentration inside the cell is higher than outside the cell, and it goes down its gradient. And by doing that, it satisfies the water electrochemical gradient issue, and at the same time, it fixes the problem for the solutes, which is they can't move. This is for non-penetrating substances. So you're both right. Does everybody get that? Yes, Leonard.
You're basically just diluting the solution with the water from the cell.
Correct. You're diluting the solution with the water from the cell. In its most basic and simplistic form. Remember, these are still very, very simple examples. Okay, is everybody with me so far? Okay, now let's go in the other direction. You're going to do this experiment one more time. You go down to 200 milliosmolar. Okay? This is considered a hypotonic solution because per square inch, there are less particles, blue particles, than there are yellow particles. Are you with me? Okay. This osmolarity is lower than what you're used to seeing for your body, by 95 milliosmolar. This is also non-penetrating substances. So the cell gets bigger. Somebody tell me why the cell gets bigger. Yeah. Water is flowing down its electrochemical gradient, which solves that issue. And then by doing that, it ends up helping the particles because they can or cannot what? They can't pass through. So you kill two birds with one stone. You fix both gradients to equilibrium because of movement of water. These are called hypertonic solutions. The tonicity says that hyper. So here's the mistake people are going to make. The mistake people are going to make is they're going to memorize stuff and they're going to make hypertonic solution. They're not going to really memorize it. They're going to sort of memorize it. Bad. Bad. Right. Walk on left side of the road, good. Walk on right side of the road, good. Walk in the middle, get squashed like great. Mr. Miyagi, Karate Kid. That's the problem here. Study, terrible, but at least you make a decision. I mean, not study terrible, study very well, good, somewhere in the middle, you get aggravated. Okay. A hypertonic solution causes the cell to do what? Shrink. Is that counterintuitive? Because you think of hyper as being more than normal. So you're thinking, if you associate hypertonic with the size of the cell directly, you're going to get it wrong. You'd be like, well, the cell got to get bigger. But it doesn't. Hypertonic refers to this solution out here. There are more particles in this one than this one. So this solution is hyper compared to that. Isoosmotics is the same. There are the same number of particles per square inch here as here, no change. This solution has fewer blue dots than yellow dots. This is all for non-penetrating substances. Okay. Now I'm going to introduce you to three other terms that are very similar. Yes, ma'am.
When you're drinking tonic water, but you know others, but what are you drinking? Is that just salt water?
I don't know. Well, what I know for sure is in tonic water is quinine, which is the chemical that's made into antimalarials. I'm not sure about the ion concentration. They figured this out by accident. People that were going into Africa and Asia during the world wars that drank tonic water were less likely to get malaria. And then they broke down the compound and found that it was quinine. So, other than that, I don't know what's in tonic water. So I don't know. All right. So everybody's okay with tonicity. All right. These three new terms deal with osmolarity directly. Okay, so an isoosmotic solution. An isoosmotic solution is a solution that, so a solution that has the same osmolarity as a cell. In this case, it's a human cell, right? So an isoosmotic solution is a solution that has the same osmolarity as a cell. You're like, oh, okay, whatever. We'll keep going. You have a hyperosmotic solution. Now your book defines it a little bit differently, but same idea. Is a solution that has a greater osmolarity than a cell. And then we have hypo. A hypoosmotic solution is a solution that has a smaller osmolarity than a cell. Now, a lot of the confusion with this is that these terms seem to be very, very similar. They are. They're very similar. That's where the confusion is. But they're not the same. Okay. So a couple of tricks about this. When you're talking about tonicity, right, the tonicity tells you something about what's going to happen to the cell. All right, essentially. And the number of particles per square inch, you can think about it that way. Okay? When you're dealing with non-penetrating substances, so the number of particles per square inch, okay, and what's going to happen to the cell, and really with penetrating, non-penetrating substances. Right? Everybody with me there? Those are three important things. When you're dealing with osmolarity, you're talking about an exact number, not relativity. If you have an isoosmotic solution and the number that we have and that you memorize is 295 milliosmolar, then an isoosmotic solution by definition, if you're exact, must then be 295 milliosmolar. This doesn't necessarily have to be. Okay? That's where it starts getting confusing. Okay? Does this tell me anything directly about what happens to the cell? If you're looking at it at face value, this is the same, this is lower, higher, and this is lower. That's all that tells you. And this also includes non-penetrating substances. Ah, that's where the ticket is. That's the problem. That's the difference. This one only includes non-penetrating substances. This one includes both. Okay, so here's one of those situations where you've got to memorize these and you've got to make sure you're clear on them. You're going to have to do them a lot to make sure you don't confuse them. It would be a travesty if on an exam you knew it, and if I had a nickel for every time someone came up to me, I knew it, but I confused them. Well, yeah, that's part of the exam. Yep.
Okay, so I have a question. So if you add isotonic cells to the body, there's no change. It says the volume. But if you add an isotonic solution, it's still no change.
An isotonic cell. Say that again. I
Like, because I just want to make the difference between like the no change volume over here. If you add the isotonic solutions to the body, there's still no change, correct?
In theory.
Okay.
In theory, and because it's dealing with it, it depends on the solution. It depends on non-penetrating substances. That's the problem. This is the simplest version. Here you have everything's like a salt. It can't, the particles can't move. Then I gave you a sheet, right? Got colors on it. At the bottom, it's got glycerol, and on the top, it's got methyl alcohol. Those are penetrating substances. That totally changes the game. Okay? So what I need you to do is to start crawling before you can walk, before you can run. Okay? And that means you've got to distinguish between these definitions. Your book does a good job of it. Okay, Max, did you have a question?
Can you just list the big difference between those bullet points?
Okay, the bullet points, the big difference, the question before. Okay, big differences. So with tonic, right, you're talking about the solution relative to the cell, but more specifically, what the solution does to the cell. So tonicity does something to the cell, right? And when you're talking about tonicity, basically the only thing that has a tone, that gives the cell a tone, are non-penetrating substances. Penetrating substances don't really affect the tone of the cell. They do, but not in the same way. Okay. When you're talking about osmolarity, you're talking about a number that is exact, right? So an isoosmotic solution, generally speaking, is exact. 300 or 290 would also be isosmotic, but again, people are going to be, but you said. So I'm trying to keep it more exact. A hyperosmotic solution then is a solution that has a osmolarity that's greater than 295. A hypoosmotic solution would then be a solution that has an osmolarity that is less than 295. And the osmolarity, in this case, also counts non-penetrating substances. So this version talks about penetrating and non-penetrating. This one only deals with non-penetrating. Yes?
When we're talking about tonic solutions, is that one referring to one soluble version that we multiple?
It refers to all of the solutes that are non-penetrating. Did you hear Leonard's question? Oh, I got to get back to your question. Leonard's question is, when we're talking about tonic solutions, are we talking about one solute or more than one solute? It's talking about all of the non-penetrating solutes. Question.
So when you're talking about osmolarity, and you say it includes penetrating and non-penetrating substances, you're referring to like any like situation like a hyperosmotic solution, the solute and the water can cross the membrane, or
Not necessarily. Some of them can.
some.
So I'm gonna take you baby steps. Okay, you're thinking ahead, which is fantastic. Okay, so I'm gonna take you in baby steps, and I'm gonna show you an example of what a question. Getting back to what Crystal asked the other day about, give me an example of what something like this looks like. Okay, I'm gonna give you an example, and then you're gonna do homework on it. All right, and that's the only way to really learn this. Yeah.
Last question, you tell me if I'm going to hydro. How do you tell if it's not penetrating or not?
You have to know. So if you can't, it's empirical, right? A chemist, a physiologist could measure it, but you'd have to know. But with what I'm going to do for you, that's why I gave you lists, right? If it is a polar large molecule that is not hydrophobic, and you know that that's the case, then it's non-penetrating, right? So a steroid hormone is a penetrating substance. Cholesterol could be a penetrating substance. Glycerol, monocetin, methyl alcohol, ethyl alcohol, urethane, urea are all penetrating substances, right? They're not like salt. Sodium can't move, but urea can. And that one is very relevant because when we get to the kidney, which is the last chapter we end up doing in this class, there's part of the cycle of how you control water in your body involves urea, and by then you're like, oh, I get it. That totally makes sense. Okay. So do you see how these little steps, how it's starting to build? I'm going slow, but now it's starting to build more and more complicated. This is still relatively straightforward if you don't understand these, if you don't memorize the difference, and you go to, I'll just keep going. I'll keep going. I'll keep going. I'll keep going. 2 days before the exam, when you're stressed out, you're not going to get them, and the day of the exam, I guarantee you're going to make a mistake. You've got to know the differences. There is no tomorrow. There is no tomorrow, right? There is no tomorrow. Everybody with me? Yeah, ask as many questions as you want. So the other question is, do we have to deal with charges? If I want you to deal with charges, it's in a relative sense, so that would be a more advanced question. So yes and no, because I would have to give you more information. But Eva's asking, we're going to have to deal with charges too. I might ask you a challenging question, but I'm not going to make it so hard that you can't answer it. So generally, I don't involve in this type of question, which comes up in the exam, a charge issue specifically. I may say, what do you think happens relatively speaking? And usually that's just a what if type question. But in order to know, you actually have to measure. That's a good question, though. She's thinking ahead. Yeah, Leonard.
What exactly do you mean by the word penetrating? What is that exactly?
A penetrating substance is a substance that can move in and out through the plasma cell membrane without a transport system and no energy involved. Yeah, Kristen. That chart is some of the penetrating substances. Now, some of them are things that you will find in your body naturally, and hopefully methyl alcohol is not something that you find in your body naturally. And ethyl alcohol is, for some of you, something that is natural because it's there so often. Okay? But nonetheless, it's not natural. In other words, your body doesn't make it normally. You're not yeast making beer.
The only thing that's throwing me off a little bit is you have with the sodium potassium, you have sodium coming in and out. So how is that not penetrating?
Oh, so Leonard's question is, with the sodium potassium ATPase, right, it's moving sodium out and potassium in. What I'm saying is that something is considered a non-penetrating substance if it needs a pump, a transporter, a carrier, a channel, or an exchanger to bypass that layer. Sodium and potassium, without the pump, without the channels, without the transporters, will never ever get through the cell membrane on their own. That's what's considered. So if you could create a system, a plasma membrane, and you can do this, you can create micelles, right? You can do this all, and then you take out all of those transport systems and you put this in solution. This is what will happen. Water can still move in and out, but the solutes can no longer because the transporters are all gone. And that's what would happen. So that it's an artificial system. Does it exactly work like this? Sort of, is always the answer. So one more point. In this class, one of the things that is very different about this class versus my anatomy class and any anatomy class is that oftentimes the answers are sort of, it depends. Because every situation changes it. That's why if you want to try to memorize every scenario possible, you're screwed. You can't. It's always maybe, if, sort of, it depends. You have to understand basic concepts and always go back to the basic concept because you can't memorize every possible scenario. You think a physician memorizes every possible scenario of everything that could possibly happen? No, they have an algorithm set that they memorize, and that algorithm tells them what to do in the next step. It's sort of the same idea here. You can't memorize everything. You can memorize a lot, but even medical students who are probably the best memorizers on the planet as a group can't memorize the phone book. It's just not possible, right? So you have to understand conceptually how things work. If you're trying to get to the details right away, that's when you're going to get in trouble. You're like, I memorized 30 things, and he didn't ask me a one of them. And then you're going to get mad at me. Okay? Does that make sense? We got a couple more minutes. I don't think, well, maybe we'll just start it. So I'll start an example. And then maybe you guys can do the homework and we can go through it. All right. So if you take out that sheet with the homework on it, I'm going to give you the beginnings of it. You're going to struggle. It's okay. It's okay to struggle. It's okay not to know. On that sheet, I have an example question. Example question, what will happen to cells if you add an isotonic solution to the human body? Okay. Okay. It sounds like an easy question, except the way I want you to answer it, it's not. If you add an isotonic solution to the human body, what's your answer? That's the answer. Here's the deal. I could care less about the answer. It's everything that comes before the answer that I'm concerned about. It's about a process. So you know the answer already. There you go. No change in cell volume. Okay, so now you have the answer. Everybody's got the answer. You're all good, right? What I am concerned about is starting to set you up on how to think about physiology. And this is your first delving into that. So you're going to tear this to pieces bit by bit. You first got to start off with, what do I know? What do I need to know? You do yeah, go ahead. Yeah, so what do we know? Yeah, so you have, so now you got to start thinking about minutia here. All of the stuff. Here's where you go from broad concept to detail. Be very detailed. What stuff do we know? For sure. Yeah, so number of molecules. Per square inch of what? Number of molecules per square inch inside ICF and ECF of what are equal? But it's got to be more specific. Of what? Read the, look at the non-penetrating substances. That's where, of non-penetrating substances. Okay, what else do you know? Now, some of this information, when you go through this process, you're not going to need to answer the problem, but I think it's a useful exercise for you to think about. Okay, what else do you know about? Now you got to start thinking about stuff you've learned. Laura. Tonicity is about, okay, tonicity is about what happens to the cell. To the cell, that's true. Okay, what else do you know? Basic information. You got to go more basic now. Yeah, Leonard and then Crystal. Okay, right, so what happens to the cell? So it won't change. So you know cell volume won't change. Cell volume will not change. Okay? Now some more basic stuff. Crystal. Well, whatever it is, because in every body, remember what I said, one of the first days is that it'll be different. But yeah, in that case, if 295, right, 295. Right, so you want to be at 295. So the cell wants 295 milliosmolar. That's where it wants to be. What else? Anything else yet? Colin? The whole system wants equilibrium, right? So system wants equilibrium. This is a really easy example. That's why you could get caught up in not giving me enough detail. What else do you know about? You got to start thinking about transporters. You got to start thinking about the electrochemical gradient. You have to start thinking about the makeup of the plasma membrane. It's a phospholipid bilayer, hydrophobic versus hydrophilic. What other information do you know? Yeah. Water can penetrate, right? Yeah, water is penetrating. Okay. What else? Go on that vein. An extension of that. Somebody else had water is penetrating. So you know water can move. Okay. What else do you know? Yeah, Alexis.
The non-penetrating needs, they need the channels and the transport.
Yeah. So right, you have non-penetrating substance. Non-penetrating substances need help. Right? They need help. They can't get across that plasma membrane, the phospholipid bilayer, without help. Okay, we're a little over, so I'm going to stop here. So what I want you to do is, what do I need to know? Okay, so here you have the answer. I mean, there's a lot. This is an easy one. All right? And then I want you to use a diagram to sort of explain this. Yeah. Oh yeah, that's right. This is the end. Sorry, I'm totally screwed up today. I have a department meeting I have to go to. I have 10 minutes. Okay, so I'm going to show you that. Even better. Thank you. I'm a little off my game today. Okay, what do I need to know? What's going to happen to the cell? See, so again, it's super easy and super obvious right now. I want it to be so because it's not always going to be that easy and that obvious. So what happens to the cell? Okay, what don't I know? What don't I know? There's some stuff, and what I mean by know, I mean for certain. What don't you know for certain? Lex.
What if the human body, if this, for example, is that 295 or is 300? We don't know.
Correct. You don't know. Yep, Leonard.
How many non-penetrating substances there are?
You don't know how many non-penetrating substances there are. Go say that again.
You don't know what the non-penetrating.
You don't know, right. So, what are non-penetrating substances? How much? You don't know the osmolarity of the solution.
Doesn't it not matter because we know it's isotonic?
Right, it doesn't really, right, that's correct. I just want you to go through the exercise. Right, you know, there's a lot of things you already know. So, you don't know osmolarity. It doesn't really matter, but you don't know what it is. Unless you measured it or I tell you, you just don't know what it is. This is how I want you to start every problem. This is obviously a really easy one, right? I picked it on purpose with the pictures up and all. When they get more difficult, this is going to pay huge dividends for you. Okay, so here's the way I like to do this. Can I erase all of this? Has everybody gotten all of this? Okay. So I like to draw these boxes, this rectangular structure that you've already seen, and I'll show you what I mean. These. Okay, we can use these and make them slightly more advanced to help you do these problems. Okay, so we're going to draw our rectangle, but we're going to draw them for the human body. Okay, what is the ICF fluid volume of your entire body? What's the intracellular fluid volume for your body? 28. We're going to use 30. What's the total fluid volume in your body, roughly? Ah, it's already coming back to haunt you. It's only been a couple of days. It's the first thing I talked about. 40, give or take. Okay. What is the osmolarity that we're going to use as norm? 295. All right, so this is osmolarity in milliosmolar or milliosmoles per liter. I don't care which one you use. It's the same thing, right? This is volume in liters. And then this is 0 down here. This is the same type of diagram, only we're making it real. We're not starting half and half, because that's not the way you're designed. So we're not going to start that way. Okay. So this is inside the cell, right? This is the ICF. And this is the ECF. What makes up the ECF? Say that louder. Interstitial and plasma. Okay. I'm also going to make this real in that, would you take a cell out of your body and put it into a petri dish? No. So if you were going to do something like this in the human, we're going to try to keep it clinical. Okay? So what would you do? I'm going to give you a big hint. I'm a really good artist. Watch. How are we going to get it in there? I'm going to give you a shot. Right? That's a syringe. Because isn't that the way you do it in a person? Or you'd stick a needle, a chronic catheter in there. Could you do it that way? So let's assume this is physiological. Let's take it out of the petri dish. Okay, so you could either do it in one bolus, meaning you can give somebody one big old shot, or you can put in a catheter with some kind of a bag. That's real, right? If you're going into healthcare and you're going to do that to people, you're going to learn how to start IVs? Sure. Well, let's keep it real. Okay. Now, did I haphazardly draw my needle there? No. Why did I put it there? Say that again? Yeah, it's got to go into the bloodstream. It's going to go into a vein. So it's got to go into the plasma first. So you're going to inject this as a bolus. And a bolus is just one big old glob of something. It sounds horrible, but it's actually a medical term. So you're going to inject this stuff in. It's like you don't know any of that stuff. You know some stuff, you don't know other stuff. Okay. You can make this roughly 150. You don't have to. Okay. So you have an isotonic solution. You know a bunch of stuff and you don't know a bunch of stuff. All right. So if you had to label this, and this is where you're going to do this at home even for this, what I want is what you know, what you don't know, what you need to know. Draw a picture. And then I want in sequence the events that are going to occur to get you to whatever the answer is. You know what the answer is. In sequence, in excruciating detail. Again, I'm trying to set you up so that you can think this way the rest of the semester. There's a rhyme and a reason to the madness. Okay, you can do that on your own. I'm just going to talk through this. Okay, so you're going to inject a bolus or hook up an IV. We can even do it this way if you'd like. There you go, saline bag. Now it's an IV. Whatever you choose. Needle, IV, whatever you want to do. I don't care. Okay, so it's going to get into the plasma. Then where is it going to go? The moon? Mars? Cops? Where? Interstitial fluid. Yeah. You can't skip that step. It doesn't magically jump. It has to go from the blood into the interstitium. That's a step. Got to write it down. Don't assume anything. Assume I'm a moron. Idiot. Got to tell them everything. Ask my wife. She'll tell you it's true. Okay? Just assume that I am one of those. You got to tell me everything. He doesn't get anything. Okay? That's the way you act. Okay. So it goes from the plasma to the ISF. Now what happens? So, okay, let's talk about what happens in the compartment. It's an isotonic solution. Okay, so you know some things about isotonic solutions. And they are what? What do you know? You have to go back to this. What do you know about an isotonic solution? Yeah, Leonard. It contains non-penetrating substances. Okay? So those non-penetrating substances that you just injected, okay, are going to do what? Alexis.
Don't they need the channel or how?
But right, now assuming they don't have any that are open. They're going to hang there. So the non-penetrating substances are going to hang there. If it's an isotonic solution, this is in the simplest case, it'll just have non-penetrating. Okay. All right. Now what about the water? Yeah, Emily.
Well, since it doesn't need channels or anything, then it's just going to stay at the equilibrium that it's at, or maintain.
It's going to maintain the equilibrium, but if it wanted to, could it move? Is it probably moving due to random chance? But in the overall scheme of things, is it going to move? Okay, so we're there. You just injected, I'm just going to add another layer to this. Into your 40 liters, you injected 500 milliliters, or 0.5 liters, just to add a slightly increased level of complexity here. Everything you've said so far is true. What happens to the size of the intracellular fluid compartment? Okay, we got one for swells. Anybody else? Yep. Yes. It doesn't change. What happens to the extracellular fluid compartment? No, somebody else other than Teresa, because I know she knows the answer. She'll save you if she has to, but what happens to the extracellular fluid compartment? Don't overthink this one. I just injected 500 mils, a half a liter of water in there. What's going to happen to that, Leonard? It's going to get bigger. By how much? 500 mils.
The volume or
The volume. Can you escape the increase in size of the extracellular fluid compartment initially, regardless of the substance you inject? Ever. You cannot, ever. You're always going to have this one do something. And if you're injecting something in, it's always going to initially get bigger. Now, that's pretty much it. This one will get bigger, this one won't change, and eventually, long term, you're going to pee it out. Isn't that what happens? You create urine, you excrete it. Now, so you can then break this problem further down into what happens immediately, short term, and long term. You see how this is starting to get more complicated? Now, when you're writing all of what I know, what I don't know, set this thing up, right? You start off with immediate, then you go to short term, and then long term, and then you go really long term, depending on how. Why am I being so prescriptive about this? This actually helps you make a better answer. If you follow these steps each time, you're less likely to screw it up. If you don't, and you go off on your own like a cowboy or a cowgirl, then you're going to have problems. Teresa?
Do you want like system changes too? Like,
No, not yet. Too early. No, forget about system. But that's where we're heading. On the final, do I want system changes? Oh yeah. But you don't know any of the systems yet, so how are you going to do that? But yes, ultimately that's where we're going. Emily?
The difference between immediately and short term for like an example like this, would you want more just like immediately like talking about the injection and everything like that, and then like short term like the equilibrium?
So yeah, that's a good question. So a lot of the fluid shifts that occur in your body can fix within a few seconds. Okay? So there's going to be things that happen within the first, let's say, minute or so. We'll define it. And then there are going to be things that take a half hour or an hour to happen. And then there are going to be things that take days, kind of like the sodium example that took a couple of days, right? So I don't care if you're exact. So here's the difference between accuracy and precision in this case. You define for me what immediate, short-term, and long-term are. Do I care if you're exactly right? No. Do I care if you sort of have a sense of what happens over days versus an hour versus a couple of seconds? Yeah. You call it whatever you want. This is where people, again, get very nervous. They're like, well, he's leaving too much to chance. Like, I don't know. What does that mean? I want you to have a general sense. Someday, you will, believe it or not, know more than I do. And if I did my job right, hopefully, you will. And you will be able to answer some of these much more challenging, very detailed questions. I don't care that you know that now. But if you don't have a general sense of, like the sodium, it takes 2 to 3 days to make an adjustment when you're taking a big load. It doesn't take 2 to 3 minutes, and it sure doesn't take 2 to 3 seconds. So you have to define that. I would work this out on your own. So go over this again with people, and then try to answer the next two. All right, there's question 1, and then there's question 2. And we will spend the majority of the next class, if not all of it, just doing this homework. Okay? I want participation. So I would come in, you can work on it in groups or individually. If I don't get volunteers, I'm going to start picking people. And you're coming up to the board and you're going to explain it. So this may be an opportunity for you to work in groups. Okay? What's that?
What do you want for Friday?
The homework. Yeah. You can definitely go back to this one and sort of finish it and do it from beginning to end and be very detailed, and then do the other two. I want one, we'll do both of them, and I want to basically talk about them all class and make sure that everybody understands how to do this. Nobody leaves here unless you know. It could be a long day. All right, have a fantastic day. Yes.
Yeah, it's the worst time, so
It's problematic, but it's less problematic.
And then so an injection of half a
Remember, when someone gets a bag, oh, yeah, if you had an injection, that would be.
Up, Dan? Walk right. Right now?
Yeah.
It's hard, right?
The problem is we go off the base. Yes, questions? Let me just shut this off because all this is being recording and you don't want to hear all of this. So. I mean, maybe you do, but my think is you don't.